Hello, welcome back to our lectures. Today we'll be looking at lipid metabolism. This particular module will be divided into 4, so we'll be starting with the first part of lipid metabolism. Catabolism of lipids, which simply means lipid breakdown. The catabolism of lipids is otherwise called beta oxidation. That's another fancy name. We call it beta oxidation. Beta oxidation of lipids, of fatty acid particularly. Of course, we know that lipids are efficient store of energy, the efficient store of chemical energy, because they contain long chains of hydrocarbons that can be broken down into very much more smaller units that can give us a lot of energy, like acetyl-CoA. So oxidation or breakdown of fatty acid is the chief source of energy, very much energy, far greater energy than you get in breaking down proteins and carbohydrates. So metabolic oxidation of lipid releases large quantities of energy through the production of acetyl-CoA, NADH, and FADH2. That is true. Because, okay, this is an example of a fatty acid. We've counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is a fatty acid with 16 carbons. So we call this what? This is palmitic acid. Palmitic acid has 16. So if you break this thing down, now what it means is that if you want to break this thing down, acetyl-CoA has only 2 carbons. So if you're going to break this thing down, if you do 16 divided by 2, you're going to get 8 acetyl-CoA. And each of these acetyl-CoA will make their way into the citric acid cycle. And each acetyl-CoA that goes into the citric acid cycle will generate 10 moles of ATP. That is a lot of energy coming from this guy. So if you break it down into this 1, 2, you break it down here, you count another 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So this typical, so if you count 1, 2, 3, 4, 5, 6, 7, 8, you're going to get 8 moles of acetyl-CoA when you break down palmitic acid. So you are getting huge amount of energy equivalent molecules and reducing equivalent that are used in making more ATP. That is why catabolism of lipid represents an efficient chemical energy store. All right, let's take it off from there. So catabolism of lipid, of course, will start from, first of all, liberating fatty acid. The commonest storage of fatty acid is triacyl glycerol. Or we can call it TG. I usually call it triglyceride or TG. Or you can call it TAG, triacyl glycerol, whichever one. So TG, let me use my usual TG. Is the main storage form of chemical energy for most organisms. Of course, in this state, like I showed you in the earlier picture, carbon is the most reduced state because each of those carbon atoms has a lot of hydrogen around it, so it is highly reduced. So the energy yield per gram of fatty acid oxidized is greater than the energy yield per gram of carbohydrate, of course. Breaking down of 1 gram of this thing gives you 9 calories. 9 calories for every gram of fatty acid. Whereas that of protein and this will give you about 4 calories. That is a huge, almost double of what you get from proteins and carbohydrate. So phosphoacid glycerol, of course, is the key component of biological membrane, and it also can be broken down into fatty acid, glycerol, and the respective other components. And the enzymes that do this are the lipases. And what is the enzyme? The lipases are specific for what? Attacking ester bond. Of course, what you find in triacyl glycerol are just ester bond. And if it involves phosphoester, if it involves those ones with phospholipid, you have phosphoester bonds too. So basically what you see in a triacyl glycerol, remember triacyl glycerol, we have 3 fatty acids esterified to a glycerol. In phosphoacid glycerol, you're going to have 1 phosphate group and then 2 other fatty acids. So this represents a fatty acid, this represents a fatty acid. So you see, this is, okay, let me use a different color. This is an ester bond. And a lipase is going to break this down. This is another ester bond. The lipase is going to act on this. This is another ester bond. Now, if you come here now, these 2 are phosphoester bonds. So a lipase is going to act on this phosphoester bond from here to break this down, to liberate this fatty acid here. And it's going to also act on this ester bond here to remove what? To remove this phosphate group. And then remember, the carbon chain here is glycerol. So we're going to see that in the next page. So triacylglycerol and phosphoracylglycerol are those common forms of lipids we're going to see. So they have fatty acid as part of their covalently bonded structure. Particularly, they are linked either through the ester or the word phosphoester bond. So the bond between fatty acid and the rest of the molecule can be hydrolyzed by the enzyme lipases. The lipases will hydrolyze the lipids, the lipids themselves without phosphate. The phospholipases will hydrolyze the phospholipids. So let's see what happens here. Now remember, both of these guys have glycerol as their main backbone. So whichever one, each of them will also give birth to glycerol. And of course, glycerol can continue to glycolysis. So look at what happens here. This is a triacylglycerol or TG. Now this TG has its own phosphate group. So lipases can break this down. Remember, lipases use water molecule to break this ester bond. So when they break this ester bond, what do? They liberate the free fatty acid, and then the glycerol goes free. Phospholipases will act on these guys. Of course, what the phospholipases do is to what? Also break the ester bond and also break the phosphoester bond at this point. Of course, since this is phosphatidylcholine, so what is it going to do? It's going to liberate the fatty acid from here. This fatty acid are going to go, and it's not going to remain a glycerol phosphoric choline, which is only from this part. And then all of the glycerol itself will continue to glycolysis. Now, the liberation or mobilization of these fatty acids by lipases is highly hormone dependent, and the hormone that acts on this is the epinephrine. Epinephrine is the main hormone, or adrenaline, if you can call it that. Epinephrine is the main hormone that actually mobilizes or liberates this fatty acid from these adipose tissue stores. And then caffeine can also mimic this. Caffeine also induces this mobilization of fatty acid, can mimic it too. And this is the reason why long distance runners often drink coffee. People who run marathon often drink coffee in the morning, so that they want to burn their fat more efficiently and spread their carbohydrate at the end of the stage when they need to speed up. Because in a fast switch, what you're beginning to burn there is carbohydrate. But at the long term, you can burn your lipids, and then in a fast switch, you can burn your carbohydrate. So let's look at what actually happens. Again, this hormonal adrenaline will act through second messenger, the cyclic AMP. Let's see what is happening here again. So again, adrenaline is a protein, is a peptide hormone. So what does it do? It binds to the receptor. It binds to the receptor on the membrane. The receptor does what? This receptor will trigger the activity of adenine cyclase that convert ATP towards cyclic AMP, and then liberating 2-pyrophosphate. Liberating pyrophosphate or 2-phosphate group joined to each other. Either call them 2-phosphate groups or pyrophosphate. And then the cyclic AMP will now activate the inactive protein kinase. Remember, kinase is any enzyme that will phosphorylate another substance or transfer a phosphate group. So what does it do? So it will activate this inactive protein kinase to an active one. The active protein kinase will now induce the phosphorylation of this triglycerol lipase. So the phosphorylation of triglycerol lipase converts the inactive lipase to the active lipase. It is now this active lipase that acts on triglycerol, this is TG, and begin to liberate this fatty acid in step 1. So the first lipase will break the first ester bond to liberate the fatty acid, and it will remain a diacylglycerol. That means two fatty acid is still there. It will break the second one, and then remaining a monoacylglycerol, and it will now break the last one to liberate the fatty acid, the last one, and then the glycerol will now move to glycolysis. Whereas this will now go to glycolysis, whereas the fatty acid will continue with the catabolism or the beta oxidation, as we're going to see. So what is the fate of glycerol liberated in this breakdown of triglycerol by lipases? Now, glycerol is converted, this happens in the cytoplasm. So in the cytoplasm, glycerol is first of all phosphorylated by ATP to glycerol phosphate or glycerol 3-phosphate. Now glycerol 3-phosphate, now this is done by glycerol kinase. This is a kinase enzyme that does this again. And then glycerol is now done what? Glycerol is now converted by a dehydrogenase enzyme. Glycerol 3-phosphate dehydrogenase will now act on this, will now act on glycerol phosphate and convert it to dehydroacetone phosphate. Remember, dehydroacetone phosphate is an intermediate of glycolysis. It is not going to get into glycolysis there, and then it will be now processed and produce pyruvate, and from pyruvate can be converted to acetyl-CoA, and then acetyl-CoA can enter the citric acid cycle and be used to generate a lot of ATPs from NADH and FADH. Remember again, because this is a dehydrogenase, so this is kinase, so the enzyme that acts here, I'm just going to write it, this is going to be glycerol phosphate dehydrogenase. It is NADH dependent. So NADH is NAD plus is oxidizing agent that accepts the hydrogen from here and now oxidizes these to the hydrogen. So what it simply did was to take away this hydrogen and make this what? Make this a carbonyl carbon. That's exactly what happens there. And then converting this to dehydroacetone phosphate, which continues with glycolysis. Now, that is how we deal with one of the products of lipase action. Now, let's talk about the main thing, the fatty acid. Now, I already told you that the breakdown of fatty acid is called beta oxidation, the catabolism. So, fatty acid oxidation begins with what? Activation of the molecule. That's the first. Remember, most breakdown starts with activation, because activation makes a reaction that otherwise wouldn't have been spontaneous to be spontaneous. So activation in lipid metabolism, what simply happens is that a thioester bond is now added to the carboxyl group to form acyl-CoA, or you can say fatty acyl. Usually some authors will say fatty acyl-CoA, fatty acyl. So what it means, a fatty acid that has this is the carbonyl carbon. It doesn't have the OH again. The OH has been replaced by CoA. That's what we meant to mean by fatty acyl-CoA. And this reaction is catalyzed by the enzyme fatty acyl-CoA or acyl-CoA synthetase. Now, this reaction requires 2 moles of ATP for this activation to take place. And then this activation takes place in the cytoplasm. It takes place in the cytoplasm, whereas the rest of the reaction takes place in the mitochondrial matrix. Remember, reactions that take place in the mitochondrial matrix is usually associated with what? Releasing a huge amount of ATP. So after the activation, the fatty acid is now transported into the mitochondrial matrix, where the rest of the beta oxidation will take place. So acyl-CoA can now cross the outer mitochondrial membrane, but not the intermitochondrial membrane. And then it's going to do this through an interesting shuttle mechanism we're going to be seeing in the next page. So this is the formation of the acyl-CoA. Now this is our fatty acyl-CoA. Remember, in fatty acyl catabolism, we told you it is otherwise called beta oxidation. And the reason why it's called beta oxidation is because I'm going to come to that. But if you're going to label this in the old nomenclature, now this is the alpha carbon, this is the beta carbon. So the next one is the alpha, beta, gamma, delta, down. So this is the alpha carbon, this is the beta carbon. Remember, in modern nomenclature, which is the IUPAC, this is carbon number 1. But in the older one, they count this as carbon number 1 and see this as an attachment. So, but we're going to be using that. This is the alpha carbon, this is the beta carbon. Remember, this is the carboxyl carbon. Now, in the fatty activation, in the acyl-CoA activation, I told you it is catalyzed by acyl-CoA synthetase. What happens there is that the CoH, which is a high activation molecule, a coenzyme, is now added to this place, and that leads to the hydrolysis of ATP to form AMP and releasing of pyrophosphate. That gives you this, forms the fatty acid. So the difference here is that we've removed this hydroxy group and now put the thioester, this is the thioester bond, and the CoA coenzyme attached to it. So this molecule is our acyl-CoA, or you can say fatty acyl-CoA. It doesn't matter whichever one you call it. To call it fatty acid, or just to say it's a fatty acid. So, but whichever one you call it, it doesn't really matter. Now, what happens to fatty acid-CoA? Fatty acid-CoA is big. Remember, these lipid molecules are very big. They're very gigantic. It cannot cross the lipid membrane. But how does it cross? It does that by having a molecule, a kind of peptide molecule called the carnitine. Carnitine is the molecule used in fatty acid metabolism to shuttle acid-CoA across the mitochondrial membrane. So let's look at this as a mitochondrial membrane. I got this picture from Wikipedia, credit to them. So this is the outer membrane. This is the inner membrane. Remember, the activation took place in the cytosol. This is the cytoplasm. Oh, I have it there written. I have it there already written. That's fine. So this is the cytoplasm. Now what happens? This is my acid-CoA. The acid-CoA has the CoA group on it. It cannot cross this. What does it do? It reacts with this carnitine, this shuttle protein or shuttle peptide. What does it do? It reacts with this carnitine and then loses its, look at what happens here. As it reacts with this carnitine, it forms acid-carnitine and loses the CoA. It loses the CoH. That's actually what's happening there. Okay, let me draw that well. Yeah, it loses the CoH molecule. So now it now forms acid-carnitine. The acid-carnitine, the enzyme that catalyzes this is called carnitine palmitoyltransferase 1, CPT1. CPT1 is located in the outer side of the outer mitochondrial membrane, the CPT1, and it is specific to catalyze the transfer of a C group from fatty acid between C14 to C16. It is very specific for it, and that is why we call it this carnitine palmitoyltransferase, CPT1. CPT1, which is located in the outer part of the outer mitochondrial membrane, catalyzes the transfer of this C group from acid-CoA to carnitine to form the acid-carnitine and losing the CoH. What happened? The intermediate acid-carnitine intermediate can now get through the outer mitochondrial membrane and then get into the intermembrane space. Remember, this is the intermembrane. Remember the structure. Oh, that's, can I write it? Oh, okay, let me make it. So this is, okay, let me use shortcut, intermembrane space. Right. So this is the intermembrane space. Now this is the matrix. So what happens? The acid-carnitine will now go through another type of transporter, which is the translocate that's located inside. So this portal is located in the inner membrane, just at the inner membrane itself. Look at what happens here. Now, carnitine, this acid-carnitine now goes through this portal, and then inside this portal, we need to recover the acid-CoA because it is the acid-CoA that will get back into the reaction. Now, so the movement of this acid-carnitine corresponds with a simultaneous leaving of this carnitine. And this carnitine leaves to replace the carnitine that have been used to formation of the acid-carnitine here. Now, but there's acid-carnitine that enters the inner mitochondrial membrane, does what again? Is quickly recovered back into acid-CoA. What happens here? Another enzyme, which we call the carnitine palmitoyltransferase 2, or the CP2, does what? Transfers this acid group and removes it again. And in that process, what does it do? It now, in that process, it now brings back the CoH and transfers it back to a C group to form the acid-CoA, and the carnitine is now free, and the carnitine can now leave again and go and replace this, and the cycle continues. So you see, the transport of this involves CPT1, which is located in the outer mitochondrial membrane, CP2, which is located at the inner side of the inner mitochondrial membrane, and then the carnitine is that particular molecule that helps this acid-CoA, to which otherwise was not permeable, to be permeable to both walls of the mitochondrial membranes. And then inside the mitochondrial matrix, the what? The beta oxidation begins to take place. The beta oxidation. I didn't get that full. So the beta oxidation takes place here in the matrix. So let's look at the reactions of the beta oxidation. The beta oxidation is a short reaction that involves a repeated series of 4 reactions. And what those 4 reactions do, the ultimate goal is to cleave 2 carbon units. Those 2 carbon units is acetyl-CoA. That's what they do. You just break fatty acid into units of acetyl-CoA. So it breaks 2 carbon units of acetyl-CoA from the carbonyl end of the fatty acid. What does it really do? Let's see. Now remember when I elaborated this earlier, this is the carbonyl carbon, the alpha carbon is alpha, this is the beta. What it does is that in the final reaction that involves an oxidation reduction, this beta carbon forms a keto group. And as it forms this keto group, what happens? Remember, this is the alpha carbon, this is the beta carbon. The enzyme which we call thiolase, the last enzyme, will now break this from here. And now form, if you break this from here, what are you going to form? You're going to form CH3C, this SCO. This is acetyl-CoA. That is the ultimate goal. And these reactions keep going themselves. So there are 4 reactions here. Now the first reaction, reaction number 1 here, is oxidation of acetyl-CoA or fatty acetyl-CoA will be oxidized to what we call the alpha-beta acetyl-CoA, unsaturated form. Now this reaction is catalyzed by the enzyme acetyl-CoA dehydrogenase, and it is FAD dependent. It's a FAD dependent enzyme. So what it means is that FAD comes in as the oxidizing agent and is reduced to FADH2. That's actually what you get. You get FADH2. Remember what we said? When you break fatty acids together down, what do you have? You have huge amount of reducing equivalent. So you get FADH2 from first one. The second reaction involves hydration. What happens here is that the beta carbon is hydrated. The beta carbon again is hydrated but with water molecule, and this is catalyzed by the enzyme. It forms, now remember what forms here initially is the unsaturated carbon. We call it the enoyl-CoA. The enoyl-CoA is now hydrated to beta hydroxy-CoA by the enzyme enoyl-CoA hydratase. And then the third reaction, this is the second reaction. The third reaction is another oxidation reaction whereby the beta hydroxy-CoA is dehydrogenated again, or is, you can say, oxidized again, because what you do is to remove the hydrogens to form a keto intermediate. And that enzyme is catalyzed by the enzyme beta hydroxy-CoA dehydrogenase. And here you also form NADH in this step. Then step 4, which is the final step, now does what? Comes and breaks this bond. Like I said, what final step does? This is the final step. Comes here and breaks this bond. This is catalyzed by a thiolase is a cleavage enzyme that comes here and cleaves the bond between the alpha and beta carbon to form acetyl-CoA, and the pathway continues. And we're going to see that in this beautiful diagram. So what is happening here? Look at the first reaction. The fatty acetyl-CoA is doing, so this is, remember again, this is the alpha beta carbon, our interest. What happens here? The first enzyme comes in, is FAD dependent, and the enzyme is called acetyl-CoA dehydrogenase. Uses FAD now that is oxidized becomes reduced. All right, so like I said, FADH here is reduced to FADH2, and then what happens? Look at what happens here. Remember, this is the dehydrogenase enzyme, and this is an oxidation reduction reaction. So you are losing 2 hydrogen. When you lose 2 hydrogen from here, it introduces a double bond between the alpha and the beta carbon to form an intermediate trans delta 2 enoyl-CoA. What is telling us here that there is a double bond formed between carbon 2. This is if you really want to count from normal high carbon molecule, this is 1, 2, between carbon 2 and carbon 3. Or you can say between alpha and beta carbon. That's what we call it trans. And it's a trans configuration. If you look at this, is a trans configuration of the unsaturated. Remember, this is unsaturated intermediate. Now, this is the first reaction. In the second reaction, an enzyme uses what? A hydratase, which simply means hydroxylation reaction, addition of water molecule. We know water is made up of OH and H, OH plus H. That's exactly what happens here. And this is happening at the beta carbon. So addition of water molecule in this beta carbon. Remember, this is the beta carbon now. So you come and add extra hydrogen and a water molecule at this point. That's exactly what is happening here at this beta carbon to form the intermediate L-beta hydroxy acetyl-CoA. Now, this intermediate is of the L configuration, but that is not so much important in our emphasis here. So what matters here is that this hydroxy group is attached at the beta carbon, which is that's what we call it L-beta hydroxy acetyl-CoA intermediate. And the enzyme that does this is the hydratase. In the third reaction, another oxidation reaction takes place, but this time it is using NAD. So NAD comes in as the oxidizing agent, accepts 2 hydrogen to form the NADH plus H, and in this case, this guy losing these 2 hydrogen now forms a keto group or a carbon in that beta carbon, in this beta carbon. So this enzyme is the enzyme that catalyzes this is the L-hydroxy acetyl-CoA dehydrogenase to form the beta keto acetyl-CoA. It's a keto acid because of the addition of this extra carbon at this beta carbon. Now, the last reaction is a cleavage reaction. This is an interesting reaction. It does 2 things. Now, it breaks the bond. Look at what happens here. Okay, I'm going to remove this my annotation here again and show you what. So look at what happens in this reaction is that this bond is now broken. Let me use a different color. I'm going to use green. This bond is now broken. You see, this is now acetyl-CoA from this side. So this bond is broken to form acetyl-CoA. And then, remember, this is a long chain. Like if it is C18 or C16 going into this, it's now going to be short by 2. So after this, if it is C18, it's going to remain C16. And that needs to go into the circle again. So what happens is that, however, if you remove this from here, the CoA is still here. But another CoA comes in and is now attached to the remaining fatty acid to form another shortened fatty acid CoA that have lost -2 carbon. That's what. So it has been shortened by 2 carbon. Exactly. That's what happens here. And this will now continue this reaction again. And this continues again. So the reaction is going to continue from here again and continues, and the cycle continues and continues and continues again. And the 4 reactions will keep happening. So this is what we call the beta oxidation of saturated fatty acid. Remember, the unsaturated fatty acid is slightly different. We're going to talk about that. So what are the important notes we need to do here? The important note we need to know is that there are 2 oxidation reactions in step 1 and step 3. There's a hydration reaction and there is a cleavage reaction. That's what we see here, the 4 reactions. What other things? There is production of an NADH in step 1. So we have NADH. Oh, let me go back to my red. There is production of NADH in step 1. No, let me make it in order. FADH first. Step 1, there is production of FADH2, which is a reducing equivalent. There is a production of, in step 3, there is production of what? NADH. And in the last step, there is production of what? Acetyl-CoA. The next question we're going to ask ourselves, how many of these can be produced? It depends on the length of what? The saturated fatty acid. And that is what we're going to address in the next page. So assuming we have a C18 saturated fatty acid, the stearic acid, that is broken down in beta oxidation. So the complete breakdown of 1 mole of stearic acid, what is it going to give us? Let's see. This is C18. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18. If you break this down, remember what I did earlier, you're breaking it down. The first one, this is 1, 2. You're going to break it down from here. You're going to have to break it down. So you're going to get what? You're going to get how many 2 carbon units? You're going to get 9 carbon units. 9 2 carbon units or 9 acetyl-CoA. And you're going to run through 8 cycles. Remember, this is the first cycle. second, third. Okay, but how can we do that? There's an easy way to do that. If you want to determine, there's a formula to determine the number of acetyl-CoA that can be determined. What you do is divide the number of carbons by 2. So this is C18, it has 18 carbons. So if I want to know the number of acetyl-CoA here is going to be 18. It has 18 carbons. Divided by 2 is going to give you 9 acetyl-CoA. That's what you get. From complete oxidation of steroids, you get 9 acetyl-CoA. Okay, how many spirals or circles can you go through? We usually call it fatty acid spiral. Spiral or circles or turns will you go. Now, how do you do that? To do that, the best thing you do is to subtract 1 from the number of acetyl-CoA. So the number of circles, I give it as the number of circles or spirals is the number of acetyl-CoA minus 1. So the number of acetyl-CoA we have here is 9. So the spiral is going to be the number of cycles or spiral of beta oxidation is going to be 9 minus 1. So it's going to give you 8 cycles of acetyl-CoA. So that's how you determine that. And then, how many NADH and FADH can you produce? Now, the number of circles or spirals is equal to the number of NADH and FADH. So what it means is that if you have 8 circles, we're going to generate how many? We're going to generate 8 in this complete breakdown of this stearic acid. We're going to generate 8 FADH2 molecules and 8 NADH molecules. And then in the next lecture, we're going to be talking about the ATP yield of complete breakdown of a particular saturated fatty acid. We're going to do what we call the ATP calculation from there. But for now, what is the takeaway? The takeaway is that you now know how to determine the number of acetyl-CoA in a complete breakdown of a saturated fatty acid. You now know how to determine the number of circles. You now know how to determine the number of FADH2 and the number of NADH. And at this point, we'll be coming to the end of this lecture. Thank you once again for listening. Bye.